Hi everybody, Philip Fulsac here. In this video, I'm going to show you how to play chess in R. As you already know, R is a programming language, and I'm using the RStudio integrated development environment to write R programs and to easily add text in R Markdown format. And thus, I'm able to generate reports. This is not a video on RStudio, but you can do lots of things. You can do plots. You can check the packages that you have installed in your environment and so on. Okay, but let's not talk about that. Let's actually see if we can play chess in R. Okay. So the outline of this activity is the following. I will first show you how to read and play chess games in R. In a second step, I will show you how to write your own chess engine. Third, we'll try to see if we could do better than a simple, very simple chess engine, and in fact get or use an oracle. And I will explain what an oracle means. And finally, I will mention interesting data sets. So let's start with the first topic, which is to read and play or replay games of chess in R. I'm going to choose a data set from Lichess that I downloaded from the Kaggle platform. The Kaggle platform is a platform for data science, contains a lot of code and data sets, and I strongly recommend you create an account there. It's a very useful website for especially if you're interested in competitions, data science competitions. So you can participate to competitions, and you can even win money if you win a prize, and so on and so on. And even better, you have lots of examples of codes and data. So I downloaded what I consider to be a very small data set. It's a data set of 20,000 games. And I just downloaded it in CSV format, okay, and placed it in my folder, and I can read it as a data frame G through the function read.csv, okay. So I'm going to read games.csv and look at the top few records. As you know, you can print the top few records by using the function head. Okay, you apply head to your data frame object G, and you get the top few records here. By default, I think the first records are shown. So you basically see, well, some fields here, some columns, ID, rated, created at, and so on. Okay. And if you want to have a better idea of what the data frame contains, here we are. You can use a structure function and apply it to the G data frame, and you'll get to know that there are 16 variables recorded in this data set, and the data frame contains more than 20,000 observations. And you can see the status of the victory, mate or resign or etc. Okay, so there are various status. The color who won the game, white or black. Okay, and the moves or plies. Actually, a move is a set of two plies when white and black have played basically. Half of a move is called a ply in chess game, and this is the so-called algebraic notation for the game. Okay, so here we are. We have now in a data frame a set of games, of chess games. Okay, not a single game, but a set of games. In fact, 20,000 games. Okay, with lots of other information. Okay. Now, what I'm going to do is I'm going to load another library just to manipulate words or strings of characters. Okay, you're going to see why I do that. And I'm going to extract the moves field of this G data frame for game one. Okay, so if I do that, so here I'm loading the library, but I'm not doing anything with it yet. But I'm actually now looking at, well, the set of moves, okay? So first, white played d4, then black answer was d5, white played c4, and so on. And of course, this notation refer to the position of the position that was played the type of piece that was played on the board. Okay, so we can unambiguously understand each move here from this formal notation. Okay, so if you want to, for example, look at what was played at the fourth fly, so 1, 2, 3, 4. You see what I do is I actually use the word function, and that word function is precisely a function that comes from the string R library, and this is why I actually loaded this library, because I would have access to such functions. Okay, so I can easily extract any particular move of my liking by using the word function and saying which move do I want, basically, okay, or which ply do I want, okay. Yeah. Okay, so now I'm going to load the RChess package, which is this library here. Of course, you would need to install it. Remember how to install a library, okay? You can do that, okay, from here. Or just, I mean, I just use a code, okay, and I just type install, okay, dot packages and so on, blah blah blah, okay, and if so, that typically should work, okay, and if RChess, if the library that you are installing, and then you run this here, you run it and it will install and finish installation and tell you that it's done. I've already done that. So once you have done it, okay, once you have read it, a good practice is to just comment out or even delete this cell of code when it's not useful anymore. Okay, so the library is already installed. I can show you that here, because if I look for RChess, okay, you can see that my RChess package is here, okay, and I have all the documentation on the package here, okay. Not so many functions, but they are quite efficient. Okay, so now what can I do with RChess? Once I've loaded my library, I can create a new game. So I can start a new game like this: chess $new, uppercase with the dash with uppercase here, and I'm going to store this game in an object called chess game. Okay, of course you can call this the way you want. If you want to call it CG or my game, doesn't matter. Okay, as long as you as you use the same name again later when you want to refer to it. Now, which color is it the turn to play? Well, it's time for white to play. Okay, we are starting the game. Okay, and now what I'm going to do, well, I know that in this game, which is the first, so I'm going actually to play the first game of G, and for that, what I'm going to do is I am going to use the move number basically, and use my word function to capture the move now. Okay, so I know that there's a maximum of 13. I'm going to play 13 times, and this is because I've analyzed the number of moves. Okay, and so I can plot the game by so I'm initializing my counter of moves to 0, and I plot my game. Nobody has played yet. I next is 0. This is my counter of moves, okay? So that's a game, okay? So under the hood, RChess calls a plotting library, okay, and you can see basically see the game, okay. And now we can plot, make the key, we can play each time we go here, okay, except if we have reached the end of the game. In other words, we are going above the number of moves played in the game, okay, as stored in the data frame G, okay. So I'm just incrementing my counter and playing the next move, okay, and then so I use the move function to tell which move to do. And the move that I do is according to the game I have stored in my data frame. Okay. So, and then once I have actually moved my chess game, I plot it. And if I'm done, I say done. So let's go. Let's play one. So here we are. White plays that. Okay. Black answers this. White plays that, and so on. Okay. So I'm going to just, you could animate easily. So yeah, this is how you can play a game. So I'm going to play the 13 moves. Okay. And yeah, I thought I could show the game, but I'm not interested in discussing the game. So here we are. I'm done. Okay. Now you must realize that, so of course you can play any game you want. It could be another game. And I want to just mention that there are two notations in chess. Okay. One is called the Forsyth notation, FEN, and the other is the algebraic notation. So they do not represent the same thing. The algebraic notation describes the moves, and the FEN notation describes the configuration, the board. Okay, the board. In other words, the position of pieces now. Okay, it's like a photograph of a photography of the board. Okay. So here we are. That's an example of FEN notation, okay, for a configuration. So basically, you have 8 rows. Each row has a sequence of symbol, and R stands for rook, N for knight, B for bishop, and so on. Q for queen, K for king, and so on. Okay, and the colors are distinguished by uppercase or lowercase. So very simple to understand. Okay. And if you have just 8 here, it means that there are 8 empty. There's no piece in this row. Okay, in row 1, 2, 3. So we show 8 empty 8 empty positions. Okay, so we can use a ggchessboard function to actually show the game from the Forsyth notation. Okay, for the FE notation. Okay, and we can, if we have a chess game, we can also plot get the FEN notation by applying the FEN function to the chess game. Okay, and here we are. Okay, that's the position we have in the chess game. Note that this is not the same chess game because here I'm plotting like I'm just applying the function, okay, but I didn't save it as a chess game. The game I'm looking at is the end game here, okay. So if you look at this here, I can again plot my game, my final game here, okay. What was the game at the end? So at the end, okay, you can just plot the chess game, and that's the end position. Okay. And yeah. Okay. So let's continue. So as I said, there are two notations, okay, algebraic or FEN, and we can easily, again, plot the chess game and extract the FEN configuration, okay. So that's kind of the photograph of the game in symbolic notation, and that's the rendering of the game in just, with the usual representation of the chessboard and the different pieces on the board, okay. Okay. So now we are done with, now that you know how to play chess games in R, okay? we could ask, okay, but can we write our own chess engine? Suppose we want a program to automatically play chess. How would you write that? Okay. So I'm going to reload a new game here and plot it. So we start again from scratch. Okay. Well, before writing, showing you how we can write our own chess engine. Okay. Let me just mention that if you type move, if you apply the function moves to the game, you get the list of admissible moves. So that's where you can play. Okay. So now, now we could ask whose turn is it to play. Okay. So to do that, we can apply the function turn. So let's apply the function turn, and we'll see who is the player now, who should play now, white. Okay, and so now if you look at that, these are all the options, if you want, available to white. He cannot move anything, he cannot do anything but one of these moves. Okay, so that's following the rules of chess. Okay, there's always in well-defined games, there's always a set of rules, and these are, and according to the rules of chess, white can only play, given that we started this configuration, these are the only moves available to white. The question is, what is the best option for white to move? Okay, so one possibility is you can write a chess engine that simply will choose a random move. Okay, so we will look at, I will use the moves function to give me the set of admissible positions that I can moves that I can play, and then I will just randomly select one move as being the move I will do. Okay, so I can easily write this function, get random move. I just take my chess game and I use a sample function to take one, one move among those moves available, which are here. Okay, so my function now is written, and you can write a very bad chess engine, but a chess engine nevertheless, which moves randomly. Okay. Okay, so here's an example. Okay, here's an example. I will actually create a chess game like this. I will initialize it with new. So I create a new board, start from scratch. And while now I can move. So I use the function game over to detect if well, I have a draw or a check. Okay, to detect the end of the game. Okay, and I play randomly until there is a checkmate. Okay, or no, until the game is over, and then I can check if there is a checkmate. But the moves may terminate in various ways. So apparently, well, with this strategy, you don't always finish with a checkmate. Okay, so let's try it. So let's try. You see here. So the random game is over. It's not a checkmate. So but so sometimes you would generate actually. Okay, here we are. Okay, so we can see that we can generate sometimes. Okay, uh, mm, a checkmate. So I'm going to just wait until I have like a checkmate and plot the game. So to plot the game, you know how to do that. Okay, you just can plot the game like this. Okay, so that's the final board. Okay, for the random game that I played, random strategy. Okay, all right. Now, what I want to do, of course, is I want to do better. So before I show you how to implement maybe a better strategy, okay, I'll indicate a few other functions. So in terms of controlling the end of the status of the game, so you can use game over to see if the game is finished. You can use in checkmate to see if the king is in checkmate, or in check for to see the king is in check, but maybe not necessarily in checkmate. Okay. So here we finished the game, and the game was over. It was a check, of course, and a checkmate. Okay, and that's why you get true, true, true for the result. And if you look at the position, well, that's the position we have, okay, in Venn notation. So that's the position of the last board, okay? Now, what you want to do is, if we want to write a better just chess engine, what we want to do is we want to write a function that calculates the value of the configuration or position, as I would call it here, okay? So, of course, a positive, well, I will just choose a convention that a positive score is better for white and a negative is better for black. It says we are playing a zero-sum game, okay? So the score of black and white will be the opposite to each other. Okay. So evaluate position is going to be the function that I will write here. And it's going to be very easy. Well, if I have a checkmate, I by convention, I return -1000 if black wins, 1000 if black is actually mate checking the white is mate checking the black, okay, and otherwise we have a draw and we return 0. Okay, so compute material advantage. So here I'm going to do a very simple evaluation. What I'm going to do is I'm going to count, I'm going to give 9 points to the queen, 5 to the rook, 3 to the bishop, 3 to the knight, and 1 to the pawn. And so I will count how many positions here are occupied by a queen, how many are occupied by a rook, and so on. It's not necessarily, even if the game starts with 2 rooks, 2 bishop, and 2 knights. Okay. Well, we can of course lose rooks and lose bishops and so on, and you can lose pieces during the game. So this number could be 0 or 1 or 2, for example, for the rooks and the bishop. The queen, it could be 0 or 1, depending if you have lost your queen or not. Okay. So basically, I multiply the number of times a piece appears by its value, and I have just a conventional set of values: 9 for the queen, 5 for the rook, 3 for the bishop, and 3 for the knight, and 1 for the pawn. I do that for the white. I do that for the black, and I compute 2 scores, black and white scores. Okay. And I add a point if I'm checking the opposite king. Okay. And then I actually calculate, I choose as my final score evaluation the difference between the white score and the black score plus the check score. Okay. So the value of the PCs of the white minus the value of the PCs of the black plus plus a score that reflects the king safety. Okay, so this is 0 if there is no check. Okay, at that in this configuration, and -1 if white is in check and the white king is in check, and +1 if the black king is in check. Okay, so now that I have my position evaluation function, I can apply it to chess game, and of course, because I know work here, I use that, okay, and black has lost. Okay, oh, mm, black has lost. Yeah. So just a sec. Well, there seems to be a lag here anyway. So just a sec. -1000. Black won. Black lost here. Well, for some reason, I get the opposite of what I should. Maybe because it's not, maybe because not too sure exactly of that, of why what's happening here. But never mind. Never mind. That's how you can calculate the evaluation of the position. Okay. There is a slight bug here, but that would be easy to fix. Okay, so minimax scoring. Now, what we want to do is we want to actually apply a strategy which is called the minimax strategy. And so the idea is this: black wants to minimize the score regardless of opponent's moves. White wants to maximize the score regardless of opponent's moves. Okay, and the best theory, the minimax theory, was theorized for the first time by von Neumann, John von Neumann, in 1928. His theory was considerably generalized by John Forbes Nash in 1958. Maybe you have seen the movie A Beautiful Mind, that tells kind of it's a fiction that tells well, the story of John Forbes Nash. Okay, as you can see, this is a very romanticized story. Okay, um, maybe not the best movie that could be done about of John Nash, but anyway. It was a very popular movie a while ago. So the idea is that we can try actually to apply the method of von Neumann and develop a function that will play minimax, the minimax strategy. The idea is exactly that one. So we need to write a routine, and this is going to be a recursive routine called minimax scoring. We calculate the score of the current board after a certain move, in fact, depth move. Okay, so we are going to go forward to a certain depth, and we are going to assume that we play minimax. Okay, the first player that calls this function wants to know how he should play, and he will play minimax. Okay, and this will deliver a list of scores. Okay, so that's how this works. So this is the name of the function, minimax scoring. You pass the game, the depth, and you evaluate if the game is over. No need to calculate a score there. Okay, and you call your minimax scoring function. Okay, and if you are white, you play the best score. If you are black, you play the smallest score. Okay. Well, that's the minimal. This is the minimax strategy. Okay. So we define this function here. Okay. And now we can write a function that obtains a move that optimizes the best score using the minimax scoring function. Okay. So get minimax move. We provide a chess game. Okay. And we look at the moves. Okay. And we actually calculate all the minimax scores of all possible moves. Okay. And well, if there's more than one optimal strategy, we just choose if we have equal scores among optimal strategies, where we choose randomly some of the moves. Okay. So here we are. We now have a get minimax move function. Okay. And we can now write a function that plays, say, 10 games. One player plays random, the other plays minimax. Okay. And that's it. Okay. So you provide the first player, well, you say which player will play minimax. And then if you are the minimax player, you play with the minimax move. And if you are the random player, you play the random move. Okay. And then you print the results. Okay. So that's how you can do this. Okay. So we can run this function here. I did that already. This takes a little bit of time, so I'm not going to rerun it here. And basically, well, I stored it. So I'm just going to show you what. No, actually, did I? No, maybe not. Anyway, so the idea, if you play this function here, if you play that function here, you will find that you will find that the player who plays minimax always win against the player who plays random. Okay. So, well, that confirms, of course, that minimax is a better game than random. Okay. Again, I'm going rapidly here because I'm just giving you the ideas. Okay. And it's up to you to try to do better if you want. Okay. So here we are. Okay. So you can see that actually developing your own chess engine is really not very difficult. A few lines of R code and you are done. Okay. The basic idea, I mean, the most important idea is the theory of John von Neumann. Okay. So that's really what allows you to actually win. Okay. So and of course you need a bit of intuition, and you have to try various techniques to maybe improve your evaluate position routine. Okay, this was a very basic one, and you can test maybe other versions. Maybe you want to take other consideration into play, okay, or into account. And so by each time you have a new evaluate position function, you can just play all the external structure of your engine works, and so it's very easy, really very easy to program a chess engine. At least from a principle, from perspective of the principle of writing it. Okay. And now, okay, so now we are done. We know how to write a chess engine. Now, how can we use an oracle? So what do I mean by an oracle? An oracle is the best chess player in the world. Imagine God playing chess, so it cannot be beaten. So does an oracle exist? Well, maybe not quite, but almost. I would say almost yes. It is a very simple program, really not very complicated, that is called Stockfish. And it's basically it has basically the same structure as I've outlined above. Okay, and it's an open source program. And so what have done here is I've downloaded this program. Anybody can do that. You can download Stockfish on your computer. I did that. So the good thing is that its Elo rating is very high. I think above 3000. Far above the rating of the best human chess players, including Magnus Carlsen, okay, which I think is around less than 3,000 if I remember correctly. And so what we will do here is we will use the Universal Chess Interface (UCI) to interact with Stockfish from here, okay, from R. So we can do lots, but I'm only going to, again, I'm just going to demonstrate this, one task, which is how to evaluate a game, okay? And the rest, how to play a game and so on. Well, once you know how to evaluate a game, the rest is kind of easy, okay? So I'm basically going to use Stockfish to replace my evaluate position routine, essentially. So to do that, what I'm going to do is I'm going to load the Big Chess package. Here we are. Okay. And there is the key function that I want to use is analyze position. Again, what's going to happen under the hood is that this function is going to call Stockfish. Stockfish is going to do the work, but analyze position will communicate with Stockfish via the UCI interface. Okay. So here we are. That's the idea. So I have stored my Stockfish engine. It's an executable binary. I'm in Windows here. So you need to do the same on your system. Okay. So you download Stockfish from the net. Okay. You go to the Stockfish website, you download the executable for your platform, you place it somewhere. Here, I provide the path of the executable of this Stockfish engine. And now I'm going to load Magritte R, and I'm going to analyze the position at a depth of 20. Imagine it. I'm going just to let the Stockfish play 20 moves ahead, okay, to get the best move, okay. So let's do that, and here we are, okay. So well, so these are the moves that are recommended by Stockfish, okay, great, okay. So I wanted to know if Stockfish is improving, in fact. So let's try and do a little bit of an exercise. If you look at the manual of the Big Chess library, this manual is here, and the manual was written in 2022, so that's 2 years ago, and it evaluates the best score of this configuration here. So I'm going to take this configuration, yes, or series of moves, configuration after the series of move here, okay. So this is what you find in the manual, okay? So I wanted to know if I repeat that today, okay, June 2024, what would I get? So let's do that actually. And the question is, has Stockfish improved? So I'm going to use the most up-to-date version of Stockfish. Okay, I first downloaded Stockfish. I did that I think last week, just to show you how to use chess in R. Okay. So can we repeat that code, and what will be the 2024 answer of Stockfish? So let's go. So I literally plug this code here, okay, and rerun that. So you see that it's very quick, okay. We are doing a very quick count here, and you can see that the best score is uh, uh, 70. In fact, I've written it, I've run that several times, and I've even got a best score of 72. So we have considerably, I would say, considerably beaten the original score. Which means that Stockfish is still improving. Okay, well, that's great. I've just showed you how to use the best player in the world from R. Okay, so which means that in R, just from R, you can beat any human player very easily. Okay. All right. Now, fourth topic. Where could I find a data set that is interesting? Well, one interesting data set that I found was from this site here. And what I did is I downloaded the 200K data set because some data sets are humongous, and this for me is like it's kind of a well-balanced data set where you have a significant amount of data, but still you can read it in a reasonable time in R. So I checked, this contains about 200,000 games, okay. It was all the games until May 2019 on Lichess. And the data set, the size of this data set is, or the CSV file is 327 megabytes. So let's see if we can read that in R and how much time it would take. So I use read CSV. I downloaded this file here, okay, and I'm referring to that data set here, the 200K data set. So let's see how much time it takes. Of course, I could time it formally, but let's just, be patient, and let's look at the efficiency of R. Is it reasonable to read this data in R? as you can see, it is still reasonable. It takes less than a minute to read. And well, now by contrast with the first data set, remember the first data set? I showed you the structure of the data. Structure of the data was here. So in the first data set, okay, in this data set, we had what? We had these many columns, okay, so 16 columns, okay. By contrast, okay, this new data set, well, first contains not 20,000 games, but 200,000, so it's 10 times bigger, okay. And second, not only that, but um, but it contains also more information. Look at the names of the fields. So here we are. Okay, so we have now not 16, but we have literally no less than, well, no less than 600 columns. Okay, so we have actually each game, okay, has 623 pieces of information attached to it. Okay, so that's a detailed data set that contains a lot of information, and you may want to use any tool that I'm discussing, say in my lectures or in class, okay, and play with this data set to do something interesting in R, okay? That's so with that consideration, okay, I would say that's all false, and that's how you can use R to do chess. Bye for now.